Welcome to another video. Our previous video looked at principal components analysis as a way to reduce the dimensionality of a data set by eliminating redundancies in the variation. In other words, we could eliminate some of the parts of our data set that are redundant and still keep a decent share of the overall variation as the original data. Today, we're going to look at a close cousin of PCA, and that is factor analysis. And while these might look similar on the outside, they're actually quite different. PCA is, as I said, a dimensionality reduction technique. It's all about trying to maximize the total variance with as few dimensions as possible, which is akin to the 80-20 rule, where maybe 20% of the original data can be preserved to keep 80% of the original variation. Factor analysis, on the other hand, is about discovering a low-dimensional set of common factors that generate the measurements that we see. And this distinction matters enormously for econometric analyses, especially as it relates to measurement error, because factor analysis is going to give us a principled way to separate signal from noise. So let's first just talk a little bit about what factor analysis is, and then we'll compare and contrast it with PCA a little bit later. If you've never heard of factor analysis before, that's all right, you came to the right place. There's two flavors of factor analysis. There's exploratory and confirmatory. And exploratory is just trying to get a sense for if there are any potential factors that are in the data, whereas confirmatory is writing down a model and then using the data to test it. As you might expect in structural econometrics, confirmatory factor analysis is going to feature prominently. And factor analysis originally came from psychometrics, which is a subfield of psychology that tries to measure human aptitude and traits and behavior. And because in our modern society, we tend to take a lot of tests either in school or for job interviews, these psychometric methods were developed to rigorously measure underlying factors that those tests were trying to elicit. And the basic idea is that each test is going to measure some set of skills, but do so noisily. And because the tests are overlapping in their scope, they're going to be correlated with each other. And so we need to make sure that we handle this multicollinearity and this measurement error appropriately when introducing it into our analysis. So let's go back to our notation from the prior video on PCA, where we have a matrix M of measurements, and there's J of these. Let's just pretend that they're test scores from some group of tests that you've taken or that the people in your data have taken. And factor analysis is going to try to find some underlying set of unobservables that commonly affect these measurements. So we're going to assume that we cannot observe these underlying unobservables data, but we can decompose our measurements. So let's just assume that we've z-scored our M matrix so that everything's mean zero unit variance. Then basically we're saying that we can attribute some of the variation in M to these factors that we can't observe, and some of it we're going to say is just idiosyncratic noise or measurement error. And so we have basically a composite error term that we're labeling U. And for now, I've kept this theta k lambda k notation from the prior video on PCA just to kind of ground your understanding. We could drop the k's and just have theta times lambda, and that's probably more appropriate, but I just wanted to kind of keep the notation analogous to the PCA video. So because we can neither observe theta nor epsilon, we have a composite error term, which you've seen in other settings of econometrics like panel data models or any other type of hierarchical model. And in factor analysis, we're going to call the theta factors, and we're going to call the lambda factor loadings, and the epsilon we will call uniquenesses. And so up till now, it looks like factor analysis and PCA kind of have a similar structure. So how are they similar and how are they different? Well, let's talk about that next. There are some important differences that we need to consider when thinking about PCA and factor analysis. As I mentioned, if we drop components from PCA, we're going to get an error term. And then in factor analysis, we're going to automatically say that the set of factors is a subset of the number of dimensions of M. So because of the covariance in M, there's some lower dimensional latent variables that are going to explain M. So that's similar to dropping dimensions. It's not identical, but in any case, in both situations, we can decompose M as theta times lambda plus epsilon. Now, this decomposition is quite different between PCA and FA. In particular, the error term in PCA is not really a measurement error. It's an error because we've thrown away information willingly. So it's more of an approximation error than a measurement error. And if we took the number of principal components back up to capital J, then this error term would be 0. However, in factor analysis, there's no way to have the same number of factors as measurements. And so we're always assuming that there's measurement error, and we're always assuming that the correlation in M is due to some lower dimensional latent factors. And so that's a philosophical difference between these two approaches. So with factor analysis, we want to separate the common variance, which is the factor theta, from the unique variance, which is the variance of the epsilons. Whereas with PCA, we just want to find the best bang for buck in terms of preserving the original variance in M. And if you want to consider more details about these two approaches, there's a great textbook chapter by Shalizi. So you can get the slide from the companion repository and then click on the link from there if you're interested. And then one other thing to consider about factor analysis is that we can also introduce covariates into our measurement system. So before I said we're going to normalize M to be mean 0 and standard deviation 1. We can also, instead of doing that, we could have just an X matrix with an intercept and maybe something else in there. And then that composite error term looks a lot like the composite error term in a regression model. So how would this work? Well, we just add X beta to our M, and then we still have this composite error term. And basically this X beta, we're going to have L columns in our X matrix. So then we're going to have, for each of our measurements, we're going to have L coefficients for these betas, and then theta and lambda and epsilon are all going to be the same. So again, here we're going to have K as being less than J. Otherwise, we wouldn't have this lower dimensional latent factor structure that we are assuming. And in this approach, we are basically just treating the residuals of M as our factor measurements. So we can just subtract X beta from M, and then this is basically interpreting the factors as being common variation once we condition on X. And that can be more palatable for certain situations. It may not be useful for other situations, so it's not like we have to include an X matrix, but it usually is helpful to residualize out certain observable characteristics that might systematically affect the measurements. So maybe one example of an X that we should consider residualizing out is age. So if I took the college entrance exam as a 16-year-old versus an 18-year-old, that might matter a lot. And so I would want to correct for that systematic covariate in the measurement system. So hopefully I've pumped you up for factor analysis and you're excited to dig in. One thing we need to be careful of is identification, because there's a lot of latency happening in our model. And so we need to make sure we put the right assumptions into our model to be able to identify what we can. And that's what we'll talk about in the next video. So specifically in the next video, we'll cover identification and how to identify the factor loadings, how to think about the scale of the variances that are in the model, and the role of exclusion restrictions in helping us interpret the results. Hope to see you in the next one, and thanks for joining this one.